Bless your heart. Some kind of way you done found yourself for the online tutoring of Mr. Whittington's. Is it Mr. or Mr.? Mr. Whit? How that man say that? Anyway, today's episode is on factories. Now, I don't know what in this Sam here any of this means, but I hope you enjoy yourself, so get your ink pen and your pencil and get ready to learn about factories.
Hello, ladies and gentlemen. This is Mr. Whit with Fort Bend Tutoring, and today's tutorial is going to be about factoring with radicals. So let's check it out. So yesterday we're factoring with radicals, and I've done something a little different with this video. I'm going to go ahead and give you a little preview. A preview of the problems that we'll be doing. Now, this is not all of the problems. Oh no, there's more. But the majority of the problems that we'll be doing in this video, let's just look at them. You have 1, 2, 3, 4, 5, 6, 7, 8 problems that you know will be covered in this video, you see? So therefore you can match it up with your work or anything like that, or to get an idea of the type of expressions that we'll be factoring in this video. All right, so there you go. A little gift from me, Mr. Whit and Fort Bend Tutoring. All right, so let's get to factoring. Here we have problem number 1. And what you should know when you're factoring any expression, and by the way, you should check out the general strategy for factoring video that we have. Matter of fact, I'll put a link right here. Okay, there you go. So basically, to sum up the video, it says that you should always look for your greatest common factor first, the GCF. Look for that first. Then you'll analyze the expression for clues as to how you should attack it. For instance, if the expression has 4 terms, then you may consider using the factoring by grouping strategy. If you have any special products involved, such as a difference of cubes or sum of cubes or difference of squares or even a sum of squares, that you should use those strategies that we have in that video. And also, you can check out our factoring using substitution video. Yeah, here's another link. There you go. All right, I'm a little link happy right here. Yeah, because that video, it goes over strategies that can be used that involve substitution to help you factor your expressions easier. Oh, yes. It's there to help. Okay. So in number 1, we should recognize that these two terms, and yes, terms are separated by plus or minus signs, that these two terms have the square root of 5 in common. Yeah, they both have that square root of 5. So we're going to factor it out, all right? But since our first term is negative here, we're going to factor out a negative square root of 5. Yeah, because no one wants the remaining factor to have a first term that's negative. It's just ugly. Why would you do that? Anyway, that's always confused me. You want your answer to look cool. Who wants an ugly answer? No one, right? So here I'm going to factor out negative square root of 5, all right? And because I'm factoring out this negative square root of 5, remember that factoring is associated with division. So in order to complete our factorization here, we're technically dividing each of our terms in the original expression by negative square root of 5. That's what's going on. So basically a negative divided by a negative is a positive, right? And so we'll end up with just 17x. Yeah, 17x for that first term, because the negative square root of 5 times 17x will give you a negative 17x square root of 5. It's beautiful. It just works itself out. Then dividing our 3 square root of 5 by a negative square root of 5, well, the negative square root of 5s will cancel out and you'll end up with negative 3. All right. And this is the answer right here. Your result is a negative square root of 5 times the quantity of 17x minus 3. There it is. So we factored the expression, using radicals. Okay, let's go ahead and red box it. See, we red box our answers here. Your answers must be in the red box. Okay, if it's not in the red box, it's just not cool. All right, let's just call it what it is. All right, it's not cool. You're not cool if you're not boxing up your answers. You got to be cool. You have to be cool. All right, box your answers for your teacher. Go ahead and show off that you know what the right answer is. I'm on to problem number 2. I'm on to problem number 2. In problem number 2 here, we have the following. We have 5 times the square root of 3 minus 15 times the square root of 6. Yeah, that's what we have. And so what we want to do is we want to first of all look for the GCF, the greatest common factor, what these two terms have in common. All right, so let's get to factoring. So first and foremost, I notice that both terms have 5 in common. They can both be divided by 5. So I know that 5 has to be part of my GCF. Oh, that is an ugly 5, isn't it? I'm going to fix it. Okay, it's getting fixed. There it is. That's better. That's better. That's a better 5. I'm much happier with that. Now moving on to the radicals, we have a square root of 3 and a square root of 6. Now, if you know anything about radicals and multiplying radicals and dividing radicals, you should know that as long as you have the exact same root, in other words, these are both square roots, right? That as long as the indexes, the roots are the same, that you can multiply them together or divide them, okay? So what I notice is that if I divide square root of 3 from both of these terms, that I can divide them evenly. That in other words, square root of 3 times square root of 2 will give me the square root of 6 here. Okay, yeah. We can even make a note of that. All right, so I'll make a note here that the square root of 3 times the square root of 2 is equivalent to the square root of 6 right here. Okay, so I'm going to use that. I'm going to keep that in mind when I'm factoring my expression. So moving forward, I know that I can also take out this square root of 3 because I've just shown that the square root of 3 is a factor of this term right here. So this is technically negative 15 times the square root of 3 times the square root of 2. So therefore, these two terms have the square root of 3 in common. All right, you see how that went? So I'm exposing the fact that this second term has a factor of square root of 3. Yeah, I'm just evil that way. All right, I just exposed it. So it's like I'm being an investigative reporter here, finding out all the dirt on that term. And the dirt is this term, this negative 15 square root of 6, it has a factor of square root of 3. Yeah, you're busted. You're busted second term. That confirms that our GCF is correct. And what remains here, remember, we're going to be dividing, all right, each term by 5 times the square root of 3 to get our result. So 5 square root of 3 goes into 5 square root of 3 once. Yeah, it does. Minus, all right, because we have 5 going into negative 15, negative 3 times. And what remains after we factor out the square root of 3 from the square root of 6 is going to be that square root of 2. So I have the square root of 2, and that completes the factorization of problem number 2. Yeah. See, if I were to multiply this back together, 5 square root of 3 times 1 is 5 square root of 3. 5 square root of 3 times negative 3 square root of 2. That gives you negative 15 square root of 6. Yes, it does. It's beautiful. Let's red box it. Red boxing it. Yeah, red boxing it. It's done. All right, let's move on. So we're moving on here to problem number 3. And in problem number 3 with this 7x squared minus 5, we're going to recognize that this form is familiar. It's similar to something that you've probably seen before. Yeah, it's called the difference of squares. But then you may say to yourself, well, Mr. Witt, this first term is not a perfect square, and this second term is not a perfect square. We can apply this factoring pattern to any quadratic binomial. Yeah, any quadratic binomial. Okay? There's no restrictions here. Who's going to stop us? No one. So no one's going to stop you. No one's going to stop us from using this factoring pattern in order to factor this binomial here. Oh, no. No one's going to stop us. So therefore, I'm going to open up a set of parentheses here, and we're going to find the square root of 7x squared. Well, the square root of 7x squared, the square root of 7 is square root of 7, and the square root of x squared is x. So we're going to go ahead and write our first term as x times the square root of 7. Yeah, that's exactly what we'll do. And then we'll have plus, using the factoring pattern here, the square root of 5 is the square root of 5. Oh yeah, we're not afraid here. We're going to go ahead and repeat this process, remember, using the factoring pattern for a difference of squares, which means that since my a term here is x times the square root of 7, I'll have another x times the square root of 7 minus the square root of 5. Oh yes, just like that. And this is your answer. That's it. That's it. So when you have a quadratic binomial, you can feel free to use the difference of squares factoring pattern to factor it. This is factored. We're done here. That's a wrap. Go ahead and red box it. Red boxing it. Just like that. You got it. That was number 3. Let's move on to number 4. All right. Problem number 4. We have x squared plus 5x times the square root of 5 minus 30. That we do. Now, in this problem here, we have a quadratic trinomial, but you obviously have that square root of 5 right there. So we're going to be using the same process that we showcased in our factoring quadratic trinomials part 1 video. Yeah, check that out. And we're going to keep in mind that, hey, somewhere along the line, guys, they had this square root of 5 in here. So we can assume, since we have an integral third term here, the last term is an integer, then that means that they squared this square root of 5 somewhere down the line. So when I look at this negative 30 here, I actually should be looking at the fact that we have this 5 separated from the 30. The only thing we need to focus on right now is the 6. We just focus on the 6 because this square root of 5, when it gets squared, that'll take care of that 5 right there within the 30. So our focus is going to be to look for factors of 6 that will subtract to give us 5. That's what we're going to do. So just to remind you, factors of 6 are going to be 1 times 6, 2 times 3, and I just need 2 of these factors of 6 that will subtract to give me 5, which is the coefficient of the middle term. Well, you said 1 and 6, right? Well, you had to say 1 and 6 because 1 and 6 will subtract to give you our middle term's coefficient. So that means that I'm going to open up 2 sets of parentheses here. All right. Your first term for each binomial will be your variable x. Why? Because x times x gives you x squared. That's why. Then, because we'll have that square root of 5 in play, let's go ahead and put that in there. Square root of 5, square root of 5. We have our variable x, multiplying to give us our x squared. We have the square root of 5 times the square root of 5 to give us this 5 right here. So now we're going to be using the factors of 6 to multiply together to give us our 6 and subtract to give us our positive 5. So that means I'll need a positive 6 right here, and I'll need a negative 1. And that's it. This is our original trinomial factor. It's over. Red boxing it. All right. For those naysayers out there, let's go ahead and get our arrows popping to prove that these binomials, when multiplied together, will give us our original expression. Recall that I said that we didn't have to worry about the factor of 5 within 30 because we knew with this integral term here that the square root of 5 would be squared eventually. Yeah. So because that square root of 5 is going to be squared, that's why it had to be a part of our last terms in each binomial. It had to. Then, because we were left with a factor of 6, we then found factors of 6 that would subtract based on that last sign in the expression to give us our middle coefficient, which is positive 5. That would be 6 and 1. All right. And because the sign of the middle term has to be the sign of the largest factor, that's why our 6 is positive, and that's why this 1 square root of 5 here had to be negative. And now we're going to multiply it out to prove that this works. So notice I already have my arrows popping here. My arrows are popping. Thank you. X times x is x squared. X times negative square root of 5 is negative x square root of 5. Positive 6 square root of 5 times x. Yeah, that's going to be a positive 6x square root of 5. And then 6 square root of 5 times negative square root of 5 will give you a negative 6 times 5. Yeah, it'll give you negative 6 times 5 because 6 times negative 1 is obviously negative 6. But then square root of 5 times square root of 5 is the square root of 25. And the square root of 25 is 5. Yeah, that's how we got the 5 right here. Okay, so from here, we're going to go ahead and simplify this. You'll have x squared. You can go ahead and just combine these middle terms here, right? Negative x square root of 5 and positive 6x square root of 5 gives you a positive 5x square root of 5. And then negative 6 times 5 is negative 30. Oh, well, that verifies that our factorization is correct. Yeah, we ended up with the original expression. It's right there. You see it right there. There's no denying this. I don't even know why you're fighting me. Okay, so anyway, number 4 is done. This is the answer in the red box. Okay, on to the next one. On to problem number 5. And in problem number 5, it looks like they're trying us again. Yeah, this is clearly a quadratic binomial. We're going to be applying the difference of squares factoring pattern. We have to, okay? So therefore, we're going to take the square root of our first term. Let me go ahead and get my parentheses opened up here because I'm about to just kill this problem. So the square root of 13x squared is going to give me x times the square root of 13. Yeah. So you go ahead and put that variable first in front of the radical because it looks cuter that way. If you put the variable behind the square root of 13, it'll look like the x may be underneath the radical sign, and you don't want that. Why confuse your teacher? Why do that? It's just rude, okay? Don't be rude. Anyway, the square root of 2 is square root of 2. Taking the square root of 2, that leaves you with the square root of 2. All right, well, it's going to be the square root of 2 here for both terms, all right? Yeah, that's what we have. And then, of course, I like to lead with a positive and then with a negative. I'm sorry, I'm an optimist, okay? Only pessimistic people put a negative first when they're doing the difference of squares factoring pattern. Why are you so sad? Be happy. Get a hug. I think there should be more hugs in the world. I'm going to go ahead and red box this. This is the result to problem number 5. Done and done. It's over. Yeah, that's pretty. I mean, you can multiply it back together to see if it works. I mean, you can get your arrows popping to make this happen. But, you know, I know it's going to work. Oh, you want me to prove it to you? Oh, Lord. Okay, fine. X times the square root of 13 times x times the square root of 13. You're going to end up with the x squared, obviously, right? And then the square root of 13 times square root of 13 is just 13. So we have our first term, that 13x squared. It's already looking good. Then from here, we'll have x times the square root of 13 times a negative square root of 2. Well, that gives you a negative x square root of 26, because with your like indexes here, because the roots are the same, you can multiply the radicands. So that square root of 13 times square root of 2 gives you a product of square root of 26. And of course, x times 1 is x. Okay. So then multiplying the square root of, oh my God, I don't even have my arrows popping. Okay. Look at you guys distracting me. The square root of 2 times x times the square root of 13, that gives you a positive x times the square root of 26. And then from there, we'll have the square root of 2 times a negative square root of 2. Well, that's just going to give you a negative 2. It just gives you negative 2. I mean, technically, you'll have initially the square root of 4 underneath the radical, but then you'll take the square root of 4, which is 2. I mean, but you already knew that. I think you're just trying me today. Okay, I really think you're trying me. The middle terms are going to cancel out. Okay, they're going to cancel. So, boom, they're done. And now, all right, let's go ahead and get this review. Thank you. We'll end up with 13x squared minus 2, and it's verified. It's done. Okay, this is the proof that our factorization is correct. All right, there you go. It's in a red box. It's in a red box. Let's move on to problem number 6. So you're just going to come in my house and just going to make me prove that the answer was right. Boy, you have some nerve on you, don't you? This is problem number 6. We have 3x squared minus 2x times the square root of 15 plus 5. Yeah, we do. Now, this square root of 15 is very suspect to me because notice that our coefficients here, 3, and the last coefficient, 5, if you were to multiply that together, you would get 15, wouldn't you? So I'm thinking that we should go ahead and do the following. Let's go ahead and open up 2 sets of parentheses here, okay? And because the factors of square root of 15 can be shown to be the square root of 3 times the square root of 5, I'm going to use those to factor this trinomial here. Matter of fact, I'm going to go ahead and say that this first term, because we're taking the square root of 3x squared, will be x times the square root of 3. This will be x times the square root of 3 here. That because of our last term, that's going to be square root of 5 and square root of 5. Okay. Because our middle term is negative, and because we have negative 2x square root of 15, both of these terms are going to have to be negative. Yeah, I'm starting to think that we are ending up with a perfect square trinomial here as far as the factoring pattern is concerned. Yeah, it's right here. That factoring pattern for the perfect square trinomial, we apply that to problem number 6. So as I stated before, all of the factoring patterns that you've encountered thus far can be applied to expressions with radicals. There's no boundaries, all right? So as long as you recognize the format, you'll be able to apply that to your expression to factor it, all right? And that's what we did right here. So this is not your answer. No, you're not looking at your answer right here. Your answer is going to be simplified into x times the square root of 3 minus the square root of 5 squared. That's exactly what you're going to have. And I'm going to red box this. Oh, yeah. It's red box now. Now, don't get me wrong. I do understand that you may not see how this answer is correct. I will prove it. Okay, here we go. Yeah, that's right. I'm not scared of you today. Most days I am scared of you, but just not today. Today, I'm feeling pretty confident. I'm feeling like I may be able to hang in there with you. Yeah, I mean, you're going to win. Obviously, you're going to win, but I'm just saying that, I can hold my own, is what I'm saying. That, I won't just be completely obliterated. Well, anyway, let's go ahead and get our arrows popping. Arrows popping. All right, and because our second term in the first binomial is negative, I'm going to go ahead and remind myself as I get my arrows popping, thank you, that second term in the binomial is negative. I need reminders. I'm sorry. So, multiplying this out. X times the square root of 3 times x times the square root of 3 gives us 3x squared. X times the square root of 3 times negative square root of 5 gives you a negative x square root of 15. Then multiplying negative square root of 5 times x times square root of 3, that gives you a negative x square root of 15. And then finally, negative square root of 5 times negative square root of 5, that gives you a positive 5. From here, you're going to combine your like terms here, all right? So you'll be able to rewrite this as 3x squared minus 2x squared root of 15 plus 5, and this proves that our factorization is correct. Yeah, that's it. It's the exact same problem. Oh, you didn't believe me again. See, the original problem matches our result. Yeah, so it works. So because we have it factored correctly and because the binomials are identical to one another, you want to combine that, all right, by showing that it's that binomial squared, and then you would red box it from there. And that's our final result for problem number 6. Let's move along. I am so glad you came to visit me today. So sweet of you. I appreciate that. So here in problem number 7, we have 2x minus 5 times the square root of x minus 12, right? And we're going to pay attention to the fact that this middle term's variable is to the 1/2 power. Well, you know how to convert a radical into exponential notation, right? Let's go ahead and do that. So first, I want to rewrite this expression in exponential notation. I'm going to rewrite it as 2x minus 5x to the 1/2 power minus 12. See, by doing this, I can show that this trinomial here is quadratic in nature. And what do I mean by that? As long as the first term's exponent on your variable is twice as much as your middle term's exponent, you can factor it as though it is a quadratic trinomial. It'll behave the same as far as factoring is concerned. So let's go ahead and do just that. And we're going to use the AC method as far as our factoring is concerned. So if you need a reminder of the AC method, the new AC method that I use, you can go ahead and check out. Once again, it's a link, I know. You can check out this Factoring Quadratic Trinomials Part 2 video. So that'll show you the process that I'm about to use. I'm going to multiply 2 times 12. That'll give me 24. Okay? Looking at factors of 24, we have 1 times 24, we have 2 times 12, we have 3 times 8, and you have 4 times 6. And you'll be looking for factors of 24 that subtract to give you 5. Well, that's just going to be 3 and 8. That's what we'll use. So your next step, you'll go ahead and open up 2 sets of parentheses here. You'll have x to the 1/2 power as your first term, because it's that x to the 1/2 times the x to the 1/2 that'll give us our x to the first power. And then using 8 and 3, your 8 has to be the sign of the middle term, so it has to be negative. So your largest factor is always the sign of your middle term's coefficient, always. And then because I'm subtracting to get -5, I need the 3 to be positive. All right. Because we have a leading coefficient of 2, I'm going to divide both of these values by 2. You got it. And then I'm going to simplify. Yep. I'm clearly having a lot of fun with this problem. I hope you are, because I am. Simplifying, we have x to the 1/2 minus 4 times 2x to the 1/2 plus 3. Yeah. See, any remaining denominators will go in front of the variable. Yeah. It'll become the variable's coefficient. Just saying. And this is the problem factored. However, you may be saying to yourself, well, Mr. Witt, I thought this was factoring with radicals. Used exponential form. Well, you're right. I'm not done. I'm going to go ahead and rewrite this x to the 1/2 power back as the square root of x. See, I just did that to make my factoring easier on the eyes. But I'm not scared. I'll go ahead and write it in radical notation. And there you have it. We have our result. It's the square root of x minus 4 times 2 times the square root of x plus 3. Red box it. Red boxing it. And there you have it. This is problem number 7 factored. You got it. Wasn't bad, huh? Pretty neat. I liked it. It was fun. Okay, let's move on. In problem number 8, we have the following problem. We have 3x squared plus 2x times the square root of 5 minus 40. Once again, they're showing us that they have a square root of 5 as a factor. So remember, that will be eventually squared because we have an integral third term. So being as though our third term is an integer, they'll square the square root of 5 to get a 5. So we're going to break this up into 8 times 5. So it's the 8 that we should focus on in our factoring process, okay? So because our leading coefficient is 3, and I have this 8 to deal with, let's multiply the 3 times the 8 to once again get 24. Once again, we got that product of 24 by using the first coefficient, and we used that remaining factor of 40 once we took out the factor of 5. So the factors of 24 are going to be 1 times 24, 2 times 12, 3 times 8, and 4 times 6. And I'm looking for 2 factors of 24 that will subtract to give me a coefficient of 2. Well, that has to be 4 and 6. It has to be 4 and 6. So let's go ahead and open up 2 sets of parentheses here to factor out this trinomial. All right. So in factoring our trinomial here, we're going to use x as our first term. We also know that we'll have the square root of 5 in play. Yeah, we will. And I'll need factors 6 and 4. The 6 has to be this. That is a hideous 6. I'm fixing it. That's no better. Really? Okay, that 6 is pretty, it's a pretty 6. All right, which really makes the square root of 5 look really ugly now, but I'm going to move on. Okay, I'm going to move on. All right, I understand that the square root of 5 is sucky, but what can you do? Because our middle term's coefficient is positive, my largest factor must be positive. Because we're subtracting the factors to get 2, the 4 has to be negative. And because my leading coefficient is 3, I'm going to simplify both of those second terms by 3. Yeah, and then in simplifying that, we'll have x plus 2 times the square root of 5. And then because the 4 and the 3 can't be reduced any further, that 3 will go in front of the variable x to give us 3x minus 4 times the square root of 5. And this is the factorization of our problem. It's done. Yeah, I'm going to red box this. Yeah, that's it. Red boxing it. I'm sensing from you little faith in my work. Okay, so I'll go ahead and prove this. I'm going to go ahead and get my arrows popping. Oh, yeah, I am. Okay, because you're trying to come for me again, and I'm not having it today. I am not having it. I'm going to prove to you that this works. X times 3x gives you 3x squared. X times negative 4 square root of 5 gives you negative 4x square root of 5. Then I have 2 square root of 5 times 3x. That gives me a positive 6x square root of 5. And then multiplying 2 square root of 5 times negative 4 square root of 5, I end up with negative 8 times 5. Yeah. See, the 2 times negative 4 gave me my negative 8. And then square root of 5 times square root of 5, it is 5. Yeah, because you have the square root of 25, and then the square root of 25 is 5. I feel like this is deja vu. Have we not talked about this already? So then we have 3x squared. Then combining negative 4x square root of 5 plus 6x square root of 5, you'll end up with a positive 2x square root of 5. Yeah, you will. And then the negative 8 times 5 is negative 40. This confirms, ladies and gentlemen, that the factorization is correct. Yeah, you'll find the correct answer in the red box because we red box it around here. Red boxing it. Thanks. Next problem. We have 4x squared plus 12x times the square root of 3 plus 27. I'm so excited about this problem because we're going to kill it. They're already showing their hand here with the square root of 3. Now, we know that the square root of 3 is not going to be a factor of 4 because 4 doesn't have any factors of 3. Okay, 3 is not a factor of 4. But it is a factor of 27. Yeah, it is. So we're going to break this up into 9 times 3. And we're going to focus on the 9. That's right. See, our square root of 3 will be squared at some point. So that means that that 3 here in our factorization can be ignored for now. And we'll focus on the fact that our first term's coefficient is 4. Our last term has this 9 in play, right? And so we'll multiply 4 times 9 to get 36. Yeah, we got 36 right here. Yeah, which is letting me know that, hold on, 4x squared plus 12x plus 9. This is going to be a perfect square trinomial, guys. Yeah, it's going to be a perfect square trinomial. Yeah, it is. Yeah, it is. You know what? I'm going to show you 2 ways to do this problem. All right, if you recognize that this is a perfect square trinomial, you can go straight to the answer by doing the following. All right, let's do this. The square root of 4x squared is going to be 2x, right? Okay. Our middle term has a positive coefficient, so you'll need a plus sign there. All right. We know that we're going to have the square root of 3 involved, correct? And we know that the square root of 9 is 3. Therefore, this is going to be 3 times the square root of 3. It's done. It's over. It's over. That's the factorization of problem number 9. Yeah, straight to the answer. That's if you recognize that it's a perfect square trinomial. If not, then this is what you can do. All right, now assuming that you did not recognize that this was a perfect square trinomial at this point right here, you can look for your factors of 36. That'll be 1 times 36, 2 times 18, 3 times 12, 4 times 9, 6 times 6, pick up sticks. All right, so therefore, I'm looking for two factors of 36 that are going to add to give me 12. Well, that'll be 6 and 6, right? Okay. So with that, let's go ahead and open up two sets of parentheses here. Okay. My first term is going to be x, all right, in both binomials. I'll need the square root of 3 in play. Yep. Go ahead and put that in there. And the two factors that are going to multiply to give me 36 and add to give me 12 are going to be 6 and 6. So those are going to be our coefficients. Both of those 6s are just dreadful. I have to fix it. Oh, that's not much better. That's not much better. Okay, we're going to move on. So since we're adding to get positive 12 as our middle coefficient here, they both have to be positive. All right. But do not fret. I am not done. Our leading coefficient, it's 4. So I need to divide both of these terms by 4 and simplify. All right. Simplifying this by 2. All right. 6 and 4 can both be reduced by 2, right? We'll end up with 3 times the square root of 3 divided by 2 times x plus 3 times the square root of 3 divided by 2. And because I can't simplify these terms any further, the remaining denominators will go in front of the variable. Yeah, that's where they'll go. All right. Let's go ahead and write our answer out. It's going to be 2x plus 3 times the square root of 3 times 2x plus 3 times the square root of 3. And since our binomials are identical, you're going to simplify your result to 2x plus 3 times the square root of 3 squared. And this is your answer. Notice how, and I'm red boxing it by the way, notice how much work was involved when you did not recognize that you were dealing with a perfect square trinomial. So recognizing patterns is a skill that is very useful when you're doing mathematics, all right? And for your survival as well, recognizing patterns. It just is. So anyway, that does it for problem number 9. It's done. It's in a red box. Twice over. We did it 2 different ways. Let's move on. Here we have problem number 10. This is 16x squared plus 7x times the square root of 22 minus 11. And what I see is a hot mess. Oh yeah. Well, let's break this down. Let's start with the radical. All right. We have the square root of 22, right? Well, fortunately for us, there's not too many factors of 22. You got 1 times 22 and you have 2 times 11. And that 11 there looks real familiar, doesn't it? So I'm going to go ahead and show that this breaks down into the square root of 2 times the square root of 11. All right, I'm going to give myself a note there that factor is going to be the result of multiplying the square root of 2 times the square root of 11. Since we have integral coefficients, the square root of 2 is going to be squared to give us 2 as a factor of 16. So this is going to be 8 times 2. So because our 2 is tied up with the radical, and because our 11 is tied up with the radical, the only number that's not accounted for here is the number 8. Let's look at 8 here. The factors of 8. We have 1 times 8, 2 times 4, and we're looking for 2 factors of 8 that will subtract. That last term tells you the operation that the factors will carry out. All right. So because it's a minus sign here, they're going to subtract to get 7. So what factors of 8 will subtract to give me 7? Do you know? Oh, well, it's going to be 8 and 1, right? 1 and 8. So let's open up our sets of parentheses here. We'll have this here. All right, give myself a lot of room to work with here, right? And I know that my first term is going to be x. And I'll need a square root of 2 on that first term. Yeah, I sure will. That's going to be the same for both. And then we'll have our square root of 11. All right, let's go ahead and throw that in there. There we go. And since our middle term is positive, we'll need a positive 8. All right. And then we'll need a negative 1 there. All right. Let's go ahead and tighten this up. Now the terms are looking much cozier. Okay. And because we were focused on that leading coefficient of 8, remember that 2 was taken out of the picture because we already have it accounted for here with our square root of 2's. We're going to divide both of these terms by 8 and then simplify. So we'll now have x times the square root of 2 plus the square root of 11 times 8x square root of 2 minus the square root of 11. All right, just like that. And that's it. This completes our problem. This is the answer right here. The answer is done. I'm going to red box it. Red boxing it. All right. And ladies and gentlemen, you have just witnessed 10 problems factored using radicals. Yeah, you did. And this completes our video. So as always, please rate, comment, and subscribe. And if you're able, please donate, as that helps us bring you more free math tutorials from me, Mr. Witt, and FBT, Fort Bend Tutoring. Peace.
FACTORING. This includes topics such as GCF, that's the greatest common factor, like Obama, the difference of squares, quadratic trinomials. Oh Lord, that's when the pig is sick on all four sides. The sum of cubes. That sounds like one of them games they play. Difference of cubes. Oh, that's just ignorant. AC method. Yes, honey, because you got to have your air conditioning in Texas. And factoring by grouping.
It's over. It's over. I know you were expecting more, but it's done. No. Calm down. It's okay. It's over now. I'm going to put a red box around this.